Okay, very good. Well, the next thing I'd like to talk about is the energy gap. Superconductors have an energy gap between the superconducting states and the normal states of the electrons. That sounds a little mysterious. Let me illustrate that with a notebook. 1 second. So here's the idea. Various experiments show an energy gap. In the density of states in superconductors. And the energy gap appears at the Fermi energy. And what I mean by that is this. If I draw a graph showing the density of states as a function of energy, I expect it to look like this. So for a normal metal, we would see something like this. And we'd also see this for a superconductor in the normal state. Let's say if its temperature is above the transition temperature. However, in a superconductor, what we see looks like the following. If the Fermi energy is here, then we see that the density of states follows the normal metal until we get very close to the Fermi energy, and then it, and then it diverges. I see I have to draw this again. Sorry, I'm going to have to move my Fermi energy here in my drawing. And let me just finish this drawing here. There we are. So a gap opens up in the density of states right at the barrier between the filled states and the empty states. And the width of the gap we call 2 times delta, okay? That's the energy gap in superconductors. And as I mentioned, there are a variety of experiments that show this. And one of the clearest is a tunneling experiment. For a system that's a superconductor connected to a normal metal through an insulating gap. And here, let's take a look at how that works. Okay, so here, first, imagine that we have something rather simple, a normal metal insulator, normal metal junction. So normal, normal, and then they're separated by a thin insulating gap. Of course, the insulating gap just acts like a resistor here. And so if we draw a graph of current versus voltage for this system, we'll find that it's just linear, like a resistor. Okay? What's interesting is what happens if we replace this by a superconducting insulating normal system. Suppose the right-hand side of here is the superconductor, and then we have an insulating gap, and then normal material. In this case, the current voltage characteristic looks quite different. what one sees is that initially, for small voltages, no current flows through the junction until we reach a threshold voltage. And at that point, the current switches on. And the threshold voltage just defines the energy gap. It defines delta. So V0 is just delta over the electron charge. Okay? So that's kind of interesting. What's going on? So what's going on in this experiment? Well, it's this. When the voltage is equal to 0, we have this situation here. In the normal material, we have a band of states that's partially filled up to the Fermi energy, as shown. But in the superconducting material, at the Fermi energy, we have a gap. Okay? So carriers cannot tunnel from the superconducting material into the normal material because at 0 volts, the states at the energy of the most energetic carriers in the superconductor, these states are all occupied in the normal metal. Okay? So nothing can happen. It's only when we make the voltage larger, V equal delta over E, that we displace the electrons in the superconducting material up in energy by that voltage, and now they can tunnel across. So it's only when the voltage is equal to V naught that tunneling can commence and we can get any current to flow. In addition, if we make the voltage the same magnitude but negative in sign, we can get a current to flow. In the following way. Give me a second while I mess around with my drawing here. So if we make the voltage have the opposite sign, once we reach a magnitude of V naught, then current can flow in the opposite direction. From the normal metal into the superconductor. But around V equals 0, we'll have an energy gap. Sorry if those drawings are a little hard to read. Here, let me show you the same thing in a PowerPoint. There we are. So this drawing represents the same drawing that I tried to make a moment ago. If we measure a current voltage characteristic of a junction like this, we expect to see 0 current for voltages below delta over E. But once we reach delta over E, then we can inject electrons from the superconductor into the metal. Or at minus V over E, at minus delta over E, we can have current flow the other direction. We just need the voltage difference to be large enough that electrons are excited either below the gap or above the gap. Here's some data that shows the same phenomenon. Note here, they're plotting the slope, di dv, as a function of voltage. So you can imagine the slope here should be positive, and then it should get very large, and then it should go to 0. Then it should get large again, and be a positive finite number after that. And that's what we see. We have a positive slope for negative voltages, then the slope increases, then it falls to 0 when we're within the gap, then it goes back up and goes back to a constant value. And what this is showing is the result of the tunneling experiment as a function of temperature. At low temperatures, the tunneling gap has its particular magnitude, and we can see the results very clearly. But as the temperature is raised towards the transition temperature, what one finds is that the magnitude of the tunneling gap goes to 0. And you can see that very clearly in the data. So that once we're above the tunneling temperature, we don't see the transition temperature, we don't see a gap anymore. Okay, so there's a piece of data that shows the existence of this energy gap between the superconducting and the normal states. Okay, here, let's stop here for a moment. All right, well, the final phenomena I want to talk about today concerns how superconductors behave in a magnetic field. Okay, and what we find is that there's always a critical field, which if we reach that critical field will destroy the superconductivity. And it's not too hard to understand why this might be. Remember, because of the Meissner effect, when we place a superconductor into a magnetic field, supercurrents will appear around the outside of the superconductor that will create their own magnetic field that exactly cancels the field due to the external magnet, so that the magnetic field inside is zero. And at some point, if we keep raising the external field, these supercurrents will have to get larger and larger, and at some point it will be energetically favorable for the material to just switch into the normal state. And that's the field where we destroy superconductivity, the critical field. But as I mentioned before, there are actually two very different types of behavior for different types of superconductor. And I'd like to talk about that for a moment. Here, hang on. Okay, so as I mentioned, there are two types of superconductors, which are called, of course, type 1 and type 2. In type 1, there's a sharp transition. And when the field reaches the critical field, superconductivity is destroyed everywhere in the sample. Okay, so we can imagine that for fields that are below the critical field, oh, I'm sorry. Oh dear. So for fields below the critical field, because of the Meissner effect, there's no magnetic flux inside of the sample. The sample is superconducting, and the magnetic field lines are pushed out. However, for magnetic fields above this critical field, superconductivity is destroyed, and the magnetic flux simply penetrates through the sample as usual. Okay? For a type 1 superconductor, a typical value of Hc1 of the critical field is about 1/100th of a Tesla. So this is kind of disappointingly weak. A material like this can't be used to make a superconducting magnet because the magnetic field would just destroy the superconductivity. So type 1 materials aren't good for that application. On the other hand, type 2 materials exhibit a different type of behavior. In a type 2 material, while at low field, just as before, the Meissner effect excludes the magnetic field from the interior. When we reach the critical field, or what we'll call the first critical field, Hc1, the magnetic field penetrates through the material but in the following form. Oh, I'm sorry. Let me just finish this drawing. In a type 2 superconductor, for fields below HC1, first critical field, it behaves just as the type 1 did. Magnetic flux is completely excluded. However, above that field, so for fields above the first critical field but below a second critical field, we'll come to in a second, magnetic flux can enter, but it enters in filaments like this. So under these conditions, between the first and second critical field, magnetic flux enters in filaments. And the core of the filament is in the normal state. And it's surrounded by a circulating vortex of supercurrent. Which cancels out the magnetic field elsewhere inside of the material. And what's important about this is the following. So this behavior will persist up to a second critical field, and then at that point, superconductivity is completely destroyed. But the second critical field, the higher critical field, is typically on the order of 10 to 100 Tesla. So much, much, much higher. And so materials that are type 2 superconductors can be the basis of superconducting magnets. Okay? Here, I want to show you a little bit of data about this as well. Hold on. Okay, it's possible to image these vortices where magnetic flux penetrates through a type 2 superconductor. In experiments that can measure magnetic fields. One way is just to decorate the superconductor with magnetic iron filings, and then they'll kind of arrange themselves around these vortices. This is another technique. In any event, this uses a scanning tunneling microscope that measures magnetic fields. In any event, you can see here these superconducting vortices. As the applied field gets larger and larger, the density of vortices gets higher and higher, as shown here. The point of this paper was to show how these vortices form a lattice. They kind of repel each other, which initially has a hexagonal structure and eventually has a square symmetry structure. That's not so interesting to us right now. I just wanted to show you that magnetic field in a type 2 superconductor can penetrate through in the form of these vortices or filaments, and that the density of filaments gets larger and larger until finally the superconductivity is completely destroyed inside of the material. All right, well, that's a quick whirlwind tour of some of the important phenomena associated with superconductivity. We've created a lot of mysteries. Next time, let's see if we can understand them. All right, well, let's stop here, okay? And I'll see you in class.